All right, so we are now heading into a chapter 6 where we're actually going to start looking at things that seem more real. So we've done equilibrium in chapter 4, looking at probably some basic structures, those things that were guide that had the wires and the cables and some derricks and things like that. But what we're going to head into here is we're going to start looking at the analysis of structures. So specifically, we'll look at 3 structure classes. All right. And those will be 1, trusses, which we'll talk about today. 2, frames, which are related to trusses but have one critical difference that we'll talk about later. And then 3, machines, which are honestly almost indistinguishable from frames, but they sort of visually look different. So that's what we're going to do. So that's what we'll do, and what we'll do here is apply some forces equals 0 and some moments equals 0, so our 2 equilibrium equations, to figure out forces in the structure. And typically, when you're designing something, you want to know what the forces are in the structure, so in the pieces of the structure, so that you can design it appropriately. All right, so what are trusses? We're gonna talk about this one today, and so some of you may not know what a truss is. So let's take a look at what some trusses are. So these are 2 pictures here, and both of these are made out of engineered wood or 2x4s or the type of stuff you'd go to Home Depot and purchase. And these are both trusses. So these are engineered floor joists. So these are laid down, and then a floor is going to go over on top of these, and then they're going to build a building on top of it. And you can see, right, you've got a series of straight line pieces. So you've got this 2x4, this 2x4, this 2x4, and they're all tied together with longer 2x4s. And so you've got a whole bunch of individual short pieces put together in some fashion to make a larger overall piece. And so the advantage here is that this is called engineered lumber building, and the advantage here is that you don't have to have a really large chunk of wood here, which you'll find out in mechanics of materials and later that you can get the same sort of bending resistance, so the same tendency not to sag when you put weight on top of it, by building it this way. So these are floor joists, and this is a ceiling or a roof joist, right? So this is designed to support a roof, right? So the roof would lie right up here. And again, same situation. You got a bunch of straight pieces connected together to form a larger structure, which is stiffer, and which you will find in mechanics of materials would be stiffer and more resistant to bending than just as it would if it was a whole solid piece, except you use a lot less material. The key point here is, right, a bunch of straight structures, and then they're fixed together at some point. Now these are fixed together with nail plates, which you can Google and figure out. But basically, they're metal plates with a whole bunch of sharp spikes on them that they hammer into the wood, so they don't allow rotation. And that's something that we'll sort of ignore when we analyze structures. All right. And finally, of course, can't leave without pointing out a couple of classic examples of trusses. Trusses are most commonly, let's get rid of that, sorry, are most commonly found for us in bridges, right? So here are 2 old bridges. Actually, that's a brand new bridge, but this is an old bridge, and you can see it's been taken out of service because they removed it, and it was probably a rail bridge. But this is exactly the same thing. Before we had I-beams and things like that, people built bridges out of pieces of steel, again, straight pieces riveted together and connected at joints, right? So again, this is just like the engineered wood trusses that we saw on the previous slide, but this time it's with steel as opposed to wood. And you can also notice too that within these trusses there are these little trusses, right? This beam right here is made up of a whole bunch of straight pieces. There's some structure up in here as well, to keep the 2 sides from collapsing inward. And again, what you get here is this gives you a structure that has a lot of resistance to this type of bending as a load is placed on it. Let's say, a train or something like that. So if there's a load sitting on here, this is very stiff and doesn't want to do this. which is good, and that's the advantage of the truss. All right, so how do we analyze these things? What's the process for analysis? And so there's some basic concepts. So for us, trusses are going to be generally 2D. So those pictures back there they look like 3D, but we're going to generally assume that they're going to be 2D. Oops, that should be a 2. Sorry. We're going to assume that the weight of each member acts 1/2 at each joint. Okay, so where that straight line piece from that truss, right, in the previous one where they were connected, the weight of that member, if we're including weight, acts 1/2 at either end, basically. And all joints are assumed to be pins. All right, so that means there is no moment at that pin. So at each one of the joints, so let's sketch out a very simple truss that's made up of just a few pieces, right? So here's a very simple truss. Again, we have probably a couple of supports on the end. And so if we were to highlight and draw the free body diagram of that joint right there, we'd have the force in this member, the force in this member, and the force in this member. All three of those members, right? So all three of the tensions or compressions in each one of those members represented by this free body diagram, right? So T1, T2, and T3. But there is no applied moment here. So each one of these members are assumed to be allowed to rotate freely about this pen. So there's nothing preventing them from rotating. That's obviously not real, right? Because if we remember back especially from the wood trusses, they were connected with these flat plates that had nails in them that definitely prevented them from rotating. But for our analysis, we're going to and design of the truss, we're going to ignore that. The fact that there's actually friction in those pin joints, right, that tend to rotate or tend to resist the temptation for this thing to rotate. And in some sense, that's our process here is more conservative because we don't have that added moment resistance within there. And then finally, the critical point here is all truss members are 2 force bodies. Okay, so if we isolate any piece of this truss, it is a 2 force body. That's all there is to it. All right. So there are 2 ways of doing truss analysis. And that is one, the method of pins. And that's where we basically just go through. So here's our truss, our simple truss that we had on the last one, right? Probably should use the line tool here. And what we do is we just go and analyze every single connection that's in this truss. So we'd go step through this, we'd find, first thing we do is there's maybe some loading here, F. We'd find the whole equilibrium of the entire truss. So we'd basically just draw the outline of the truss, draw the free body diagram, and figure out the reactions. And then we'd start taking the truss apart, drawing the free body diagram here, the free body diagram here, and the free body diagram here, just stepping through each one. The second option is called the method of sections. All right. And in this method, this is really good for getting at forces in in interior pieces without having to step through solving the entire thing. So let's say we're only interested in the force in this member right here, right? So to get at that one by method of pins, we'd have to solve this joint and then solve this joint or this joint. That's how we'd have to do it. With method of sections, what we're going to do is we're just going to cut the entire body. So I'm going to make a cut right there. Like I'm going to cut it with a knife. And then I can draw the free body diagram of that cut and have it basically just represent all the cut pieces with forces. Right, so if this was part A, this was part B, this was member A, this was member B, and this is member C. We just represent all of those, and then of course we'd have a reaction here, right, at B. No, not B, sorry. Let's call that D. Right, so that would be D, that would be that reaction. And then we draw this, we do this this solution right here. And so that's how we do method of sections. For your homework here, basically we're going to focus entirely on method of pens. So let's step through method of pens in a little more sort of just the solution process. So method of pens, solution process. All right, so let's draw again a simple truss, and I'm going to do this with the line tool now. All right, this is sort of uneven truss, but that's all right. All right, so first step is global equilibrium, right? So we've got a truss that's got a couple of supports, right? And then let's say it has some loading on it. F1, F2. Could be a distributed load, could be a whole bunch of other stuff, but we'll just keep it a couple concentrated forces to begin with. All right, so first thing we want to do is draw the free body diagram of this thing. Of the global free body diagram, right? So, oh no. Wish that worked. All right, so the global free body diagram would basically just looks like this. We're going to ignore all the internal structure and we're only going to look at this equilibrium of the exterior, right? So we would have the two reactions here. We'll call this A and B. All right, and then our two external forces, F1 and F2. And then we just solve this. So we treat this whole truss as a body and solve for the reactions at A and the reactions at B. And then once we have those reactions, then we start disassembling the body. So if we have all those reactions, we can then pick a point to attack. Doesn't matter. You just basically have, again, you're sort of just like I talked about before, you're propagating known information. So you know information here and you know information here due to the fact that you solve for the reactions here, and you just have to make sure you pick a place that has less than 3 unknowns, right? So here you have both reactions and you don't know these two pieces, so we can just start at A. And so you take A and you draw the free body diagram. So you would have a reaction in the Y. Obviously we have no reaction in the X from that previous one. And then you basically just pick, so here's A, we'll call this C, D, E, just to begin with. So this would be T, AC, and then we'd have another reaction T, AD, right? And that's the only two forces, right? So there's only two members, so there's only two forces plus the reaction. And then you'd solve that, right? There's only two unknowns, so you can do some forces equals 0 and get to TAC and TAD. Then you pick another point. You pick this point, let's say. Draw the free body diagram of that. It would look similar to this. And then you'd move to D, and then E, then F, then G, and then you'd have all of them and they'd be completely solved. The geometry for these angles, theta, are typically given to you because you're typically given this dimension, h, and then typically this dimension, l, and then some information about these lengths right here. So you'd be given these type of information to solve the problem and to solve the geometry. And that's pretty much all there is to doing method of the joints. And this will become real clear when we do more examples in class.